friend. I'm doing my thesis on Dr. Hami Sarisara. I'm a graduate student from electrical engineering. I'm going to introduce you all to our research work on high throughput field phenotyping of plants. Let me begin my explanation with a thought-provoking question. World population is likely to exceed 9 billion by 2050. Will we be able to meet the food needs for the increased rapidly growing population? As a matter of fact that we have fixed land and other resources, we should soon be able to figure out efficient methods to multiply food production with the limited resources we have. Can you go to the next slide? Let me first of all tell you what exactly phenotyping is. Whenever research scientists from plant sciences come up with a new plant trait, that is a new genotype, they grow that particular plant out in the field and they tend to see what are the plant reaction to the environment. That is called a phenotype. The reaction of a plant to its environment is called a phenotype. Can I move to the next slide? Unfortunately, there has only been significant improvement in genotyping methods, but there hasn't been any significant progress in phenotyping techniques so far. So just to give you an idea about the dimension of the problem, if you consider this simple example, let us assume a mapping population of 25 crosses, each represented by 200 lines. That gives us 5,000 lines. And if you want to have two replications, that gives us 10,000 plots for treatment. And say you want to treat all of these with dry land and well irrigated land, that leaves us with 20,000 plots. So considering a single row, all this arrangement could probably take up to 50 miles of line. Growing.
So explain what lines are.
Lines, they are basically, say if you say parent A and parent B, when you cross parent A and parent B, you get the next generation F1. When you self-cross the child with itself, you get next generation F2. These lines basically consist of the self-crossed children of the same.
I just wanted you to explain that.
Yeah. Can you go to the next slide? So a person walking at 3 kilometers per hour would probably need 27 hours just to visually score all the information, assuming no stopping. Say if the same person stops 30 seconds at every plant, he would probably need 167 more hours, that is approximately 7 days more. So this simple problem statement gives us an idea about what the need for going to high throughput phenotyping. Yeah. So our project goal is basically to devise and develop a robot which is capable of concentrating an individual plant out in the field. So it should be able to keep track of individual plants out in the field and go to the same plant repeatedly again and again and store the data and give the data to analysis for biotechnologists and breeders. So let's see what is the state of the art in this particular field. So basically there has been a significant improvement in greenhouse phenotyping. I must say University of Wisconsin has been really active in greenhouse phenotyping. Lemnatech is a leading company from Germany. They have been playing a very active role in phenotyping in the greenhouse. They were able to successfully focus on individual plants for phenotyping, but the problem with greenhouse phenotyping is that environment conditions in greenhouse differ largely from those of the conditions outside in the field. So if you can go to the next slide. So if we look into the field scale progress, we have a research scientist from Arizona. They have actually devised a tractor which goes into the field and takes a look at plants and takes measurements of the various traits of the plants. They are actually able to concentrate on individual plants, but the problem with this heavy tractor moving in the field is that this particular heavy machinery may lead to compacting of the soil, which may lead to stress on the plants, additional stress on the plant. We don't want that to happen. Okay. say this is another research scientist. He has come up with a phenocopter. This phenocopter actually goes over the air and tries to have various measurements of the plant. Problem with this particular phenocopter is that it is not capable of keeping track of individual plant. It looks at a plot as a whole, but it does not give us the information about individual plant. And as you can see, it is difficult to operate this particular phenocopter in all weather conditions. It's difficult to operate, and it becomes more costly as well. Yeah. Coming to our, can you please plug the cable properly? No. So coming to
it looks perfect here.
Okay. Coming to our tool, we have actually we got a customized robot solution from Corover Robotics Incorporated from North Carolina. We have a nice little robot that is capable of carrying all the sensors, that is capable of going into the field in any weather conditions, especially that is resistant to Texas extreme weather conditions. So we just got this robot today. Can you go to the next slide, please? So coming to the various problems to solve, as you can see by the scope of this project, this is a multidisciplinary project. You see a lot of tasks involved in it. To begin with, the basic task is navigation. To concentrate on individual plants for phenotyping, the localization accuracy required is less than 2 centimeters. And we should be able to first of all detect a plant. After detecting the plant, you should be able to recognize the plant. Say, this is plant A, this is plant B, and when it goes to the same plant tomorrow again, it should be able to say, this was the plant it looked yesterday. Yes?
So now I assume you don't want to put markers on all these plants too?
Absolutely not. That was one of our intentions. We don't want to do anything artificially onto the field. So yeah.
Artificially on the field is okay, on the plant is not.
Artificially, we don't want to illuminate the field in any way. We just want to keep the field as it is and come up with the best solution.
How about RFID?
I'm sorry? RFID, we initially thought of RFID tags, but if you look at the figures that I've given you earlier, attaching RFID tags to 50,000 plants is practically not feasible. 50,000, yes. So, this is basically a brief overview of navigation tasks. We should be able to detect a plant and we should be able to recognize the plant. I hope you got the difference between detecting and recognizing. Thank you. Next slide. And the next important task is imaging. We have various imagings that can be done on the plant to get variety of information. Say these are the infrared images of a leaf taken. Basically, infrared imaging of leaf gives us the moisture content and moisture distribution of the plant. You can see the moisture distribution all over the plant. So this is just an example of getting one trait of a plant. What if you want to see some other information? We have hyperspectral cameras, we have X-rays, and we have a lot of stuff to study the plant. So imaging is another challenging task on the robot. And the next important task is data handling. As the robot moves out on the field, we have enormous data generated. So we should be able to make a choice. If I want to go to the next step, you should be able to process some of the data before you ship it to the warehouse. So you should be able to figure out what is the data that needs to be processed on the board and what is the data that needs to be shipped over to the base station to be taken care of. That needs to be stored in the database. And even this shipping has to be done in an efficient way, and storing of the data, compressing it, that needs to be done in an efficient way. As I told you, we should be able to trace the data back until its first generation, A and B. Say, if you notice some interesting feature after 5 generations of crossing, if you notice some interesting characteristics of the plant, using these data links, you should be able to pull out where this particular child came from. What is its root parent? Did you get what I'm saying? So that's basically all the challenging tasks related to data handling. No, next slide. As far as my association with this project goes, I'm totally concerned to navigation tasks. So let me go a little bit deeper into navigation tasks. As I told you earlier, we need localization accuracy of less than 2 centimeters to detect individual plant. So how do you think we get localization accuracy of 2 centimeters? That's a challenging task. And you know, plant mapping again, detect the plant and store its coordinates in its memory, so that when it comes to the same plant again, it says this is the location corresponding to this particular plant and this corresponds to this plant. Then go to the next slide. So we have actually assembled a RTK GPS system which consists of 2 GPS receivers instead of 1. What we have basically is, other than regular GPS receiver on the robot, we even have a GPS that is located at a fixed reference known location. So basically, the accuracy of our regular GPS systems is around 5 meters. So basically, accuracy of the GPS is determined by various other factors like environment, distortions in layers, ionosphere, troposphere and all. So if we can somehow figure out the distortion, we can apply that distortion to the road. Since this base station is in a known location, we calculate the distortion of